Hello. This video includes information on the second and third laws of thermodynamics and Gibbs free energy.
When we talk about changes in entropy, we're actually talking about different things that we need to consider altogether. We're going to be talking about the entropy of the system, which is what we're actually studying, and the entropy of the surroundings, which is essentially everything else. And the entropy of the universe, the total disorder in the universe, equals the sum of the entropy of the system plus the entropy of the surroundings. Now, a process is spontaneous if the entropy in the universe is increasing, if the entropy in the universe is positive. So if the entropy of the universe is negative, if the overall disorder in the system, in the universe, in everything, is going down, the process is non-spontaneous. That doesn't happen. Okay, the universe overall is increasing its entropy. And if the entropy change for the universe equals 0, that means the system that we're studying is at equilibrium. So you can spontaneously decrease the entropy of a system, like freezing something, if and only if you also deal with an increase in entropy for the surroundings. And the increase in entropy for the surroundings has to be greater than the decrease in entropy of the system. In other words, if this value is negative, this value not only has to be positive, but has to be positive and bigger than this number so that the overall entropy change for the universe remains positive. So let's look at kind of some scenarios for a second. Okay, let's say that we have our system here, okay, and this is our surroundings here. We always kind of have to identify what our system is versus everything else. And in our first scenario, our system is at a lower temperature, and we have energy being transferred from the system to the surroundings. Okay, well, if we look at the system first, the system's losing energy. And our temperature is always going to be positive because it's always going to be in terms of Kelvin. And Kelvin is an absolute temperature scale. So this value for the entropy change for the system is negative. Okay, the system is losing energy. The particles are going to be more ordered in the system. If we were to look at the surroundings, well, in this scenario, the surroundings are gaining energy. So the entropy change for the surroundings is positive. Now, the system's entropy is going to be changing at a much greater magnitude than the surroundings are. So the overall entropy change for the universe would be negative, and that's not possible. Well, energy isn't going to flow from low to high. That makes sense that our delta S value is a negative value, is less than 0. So now let's look at the next scenario. So now we've got our system here. We've got our surroundings here. The surroundings are at a higher temperature than our system, so hotter, colder. And this time we want to study energy being transferred from the surroundings into the system. So that means that the system is gaining energy. Q is positive, which means the amount of energy or the entropy change for the system is positive. Well, the surroundings are losing energy, so Q is negative. Our entropy change is going to be negative, but again, because the system is so much smaller than the surroundings, this is much less significant a change. So our system is positive. Our surroundings are negative. The positive supersedes that negative value. So in this case, the entropy change for the universe overall is positive. Well, energy flowing from high to low makes sense that it's going to be an increasing entropy value. Now, this third value, we have our system here, and we have our surroundings here. And this time, the system and the surroundings are at the same temperature. Energy being transferred from the system to the surroundings. So the system would have a negative Q. The surroundings would have a positive Q, but the temperatures are the same. And if the temperatures are the same, this value is equal and opposite to this value. And our delta S for the overall universe is 0. We're actually at equilibrium. Energy isn't going to flow from the system to the surroundings. The only scenario out of these three scenarios that's actually going to be spontaneous would be this middle scenario where energy Q is being transferred from the hot universe into the cooler system. Let's ask a question, and we'll do a little bit of math to kind of show it. Okay. Why does water freeze below 0 degrees, but it doesn't freeze above 0 degrees? If we were to look at freezing, okay, we're going from a liquid to a solid. So the randomness or the disorder or the entropy for the system, the water, is going down. So delta S for the system is going to be less than 0. It's going to be a negative value. Now, if we talk about going from a liquid to a solid, the system is losing energy to the surroundings. That means that freezing is an exothermic process. So the surroundings are going to be gaining energy. Energy is going to be flowing from the system to the surroundings, which means that the particles in the surroundings are going to be at a higher temperature, which means they're going to be at a higher entropy, which means that entropy change for the surroundings is going to be a positive value. Now, if we were to look at the overall energy in the universe relative to this change, the delta S for the system is the entropy change when we have a liquid going to a solid. And the delta S for the surroundings can be calculated by taking Q divided by T. Now, when we talk about entropy, entropy is in the term of joules per Kelvin. So that means that if we were to increase the temperature, that's going to decrease the entropy. They're opposites. So an increase in entropy of the surroundings is inversely proportional to its temperature. So what does that mean? If we're at a lower temperature, the surroundings are going to be at a higher entropy. So here's our system here. Okay, it's a negative entropy because we're going from a liquid to a solid. Here's our surroundings here. The overall universe is the sum of these two values. And at a low enough temperature, the surroundings will have a larger entropy change than the system will. That'll leave us with a positive entropy change for the universe. That means this process is spontaneous. So water will spontaneously freeze below 0 degrees Celsius because at lower temperatures, the entropy of the surroundings is greater than the entropy change for the system. But if we're at a higher temperature, if we're above 0 degrees Celsius, a higher temperature means a lower entropy for the surroundings. So our entropy change for our surroundings will be less than our entropy change for our system. And the sum of these values will give us a negative delta S for the universe. A negative delta S for the universe means the process isn't spontaneous. So at higher temperatures, the entropy change for the surroundings is not enough to negate the entropy change for the system to make the overall entropy change for the universe a positive value. So in other words, water does not freeze spontaneously above 0 degrees Celsius. So let's do a quick calculation now. Okay, if we look at solid water, ice, and we change it to liquid water, so we're melting water, the entropy change is 22.1 joules per Kelvin. Now, this is a positive number, and that makes sense because liquid water, the particles in liquid water are more random, less ordered than the water molecules in the solid state in ice. So it makes sense that this number is positive. So 22.1 joules per Kelvin is the entropy change when we melt water. Okay, it requires the surroundings to transfer 6.00 kilojoules of heat into the system. So we have to absorb energy in order for this melting to take place. Is the process spontaneous at -10 degrees? And is the process spontaneous at +10 degrees? So let's mathematically calculate that. So here's our equation. Okay, so let's look at -10 degrees first. Delta S for the universe, which is positive for spontaneous and negative for non-spontaneous, equals the entropy change for the system plus the entropy change for the surroundings, which can be calculated by taking the heat and dividing it by the temperature. So it gives us the entropy change for the system, the 22.1 joules per Kelvin. It gives us the energy that has to be transferred from the surroundings to the system. And it gives us the temperature. -10 degrees Celsius is 263 Kelvin. Now, notice the sign on Q. It's a negative value because the surroundings are losing energy to the system. So the surroundings are losing this much energy to the system at this temperature. Collectively, that gives us the entropy change for the surroundings. So when we plug this into the calculator, we're going to get -0.714 joules per Kelvin. That means that the entropy change for the surroundings is not enough to supersede the energy change of the system, so it's not spontaneous. We're not at a high enough temperature. What I want you to do is calculate delta S for the universe at +10 degrees Celsius and see what you get for that delta S for the universe and decide whether water can spontaneously melt at 10 degrees Celsius. Okay, so we're still using that 22.1 for the delta S of the system. Okay, that's the entropy change when solid water changes to liquid water. We want to find out what the entropy change for the surroundings is. Notice that the Q value is the same, but now the temperature is 283 Kelvin. Yeah, I agree. It's a positive number this time, 0.899 joules per Kelvin. So that means the process is spontaneous at a higher temperature. So all this does is it just quantifies the graph we were looking at before. So if we're at a lower temperature, the entropy change for the surroundings is not enough to cancel out the system, but if we're at a higher temperature, it is. So we get a positive value, it's spontaneous, as opposed to at a lower temperature, it's a negative value, so it's not spontaneous. All right, so we're going to look at one more question, I think, and then we'll take a quick break. So when we talk about Q, we know that Q means heat or energy transfer. So Q for the surroundings equals negative Q for the system. In other words, if the system is losing energy, the surroundings are gaining that energy. And Q for the system is also known as our enthalpy change, as long as we're at a constant pressure. We know that delta S for the surroundings is calculated by taking the energy change for the surroundings and dividing it by the temperature. We can just do a little bit of substituting. For Q for the surroundings, we could substitute in negative Q for the system. And for Q of the system, we could substitute in delta H. So delta S for the surroundings equals negative delta H divided by T. So the entropy change for the surroundings will equal the negative enthalpy change for the system divided by the temperature of that system. So let's look at an example. Let's say that we have this reaction here. We're told that delta H equals negative 125 kilojoules. The negative means that this process is exothermic. We want to calculate delta S for the surroundings at 25 degrees Celsius. So this system is giving off energy to the surroundings. How is that going to affect the entropy of the surroundings? So negative delta H over T is the equation we want to use. Now, if delta H is negative 125, negative 125 gives us positive 125. So 125 divided by 298. Again, we want the temperature in Kelvin, so we're just adding 273 to 25. So that gives us 0.491 or 491 joules per Kelvin. This is a positive delta S value for the surroundings, and that makes sense because the system, which is this reaction, is giving off energy because it's exothermic. So the energy is flowing from the system to the surroundings, which means the particles in the surroundings have more energy after this reaction, which means the particles in the surroundings are going to have a higher entropy, a positive delta S value. Okay, so let's do another problem. Okay, see if we can follow what we did before. So we want to calculate the delta S for the surroundings, the entropy change for the surroundings, when we look at this reaction here. Okay, same kind of problem, except that delta H this time is a positive value. That means this reaction is endothermic, which means the system, which is this reaction, is absorbing energy from the surroundings. So the surroundings are losing energy this time. So calculate your delta S for the surroundings for this reaction. This system is endothermic, okay, a positive delta H value, which means that our surroundings are losing energy. So negative 778 kilojoules divided by 298 Kelvin. And again, we want that in terms of our absolute temperature scale. So we're just adding 273 to 25. So we get negative 2.61 or negative 2,610 joules per Kelvin. Again, the important thing is this negative sign, because if our entropy for our surroundings is negative, it means that the particles in the surroundings are becoming less disordered, or the entropy is going down. And that makes sense because the particles in the surroundings are losing energy when we look at an endothermic process. So when we talk about entropy, okay, by definition, the entropy of a perfect crystalline solid at 0 Kelvin is 0. What does that mean? Okay, well, it means that if we're at 0 Kelvin, there's only one way for the particles in that perfect crystal to be arranged, because the particles essentially have no energy. They're not moving around anywhere. They can only be in one place. So if we were to plug that into our equation, the natural log of 1 is 0. So the entropy is 0. Entropy values for everything else is measured against the absolute 0 of entropy. As the temperature increases, the entropy increases. And we can use these values to do calorimetric measurements. So when we talk about our entropy values, we're going to be looking at values at 0 Kelvin to 298 Kelvin at 1 ATM. And we're going to be dealing with what's called the standard entropy changes for these substances. So if we were to look, it's just on a table. Let's kind of just look at some of these numbers. You would never memorize them. You just have to know what to do with them. But let's take a look at some of them. Like if we were to look at, let's say here, we've got gaseous water versus liquid water. Okay, well, gaseous water has a higher entropy value than liquid water. That makes sense. If we were to look at C2H5OH and compare it to CH3OH, okay, C2H5OH is a more complex molecule. It's going to have a higher entropy value than CH3OH would be, just to give us some general ideas about what those numbers are. So what are we going to use that for? We can calculate the entropy change for a reaction. And we do that by taking the total entropy change for the products and subtract the total entropy change for the reactants. Now, the V stands for the stoichiometric coefficient in the balanced equation. Okay, it just means the coefficients when you write your balanced equation. This is a sigma sign, it just means the sum of. So what we would do is take the entropy values for the products in a chemical reaction, multiply them by the coefficient in the balanced equation, because these values are per 1 mole, and perhaps you have more than 1 mole in a balanced equation. And then you would add all of the products together. And that's what would go here. And then you'd take all of the reactants, multiply them by the coefficient in the balanced equation, and add them together. And that would give you the sum of the entropies for the reactants and subtract that from the products. So here's kind of an abbreviated table over here, just for things that we need in these questions. So we want to calculate the entropy change for these two processes. So let's look at A. We'll do A together, and then I'll have you do B on your own. So first thing we do, which we should do for all problems, is write down the equation. So here's our equation. The entropy change for the reaction equals the sum of the entropy changes of the products minus the sum of the entropy changes for the reactants. So for A, we only have one product. It's gaseous water. So we would take gaseous water. So 188.71 times 1, because the coefficient here is a 1. And there's only one product, so that's what would go here. And then we'd look at our reactants. We've got liquid water. We find liquid water over here at 69.91. And there's a 1 for the coefficient here. So 1 times 188.71. Okay, now this is kilojoules, or sorry, joules per mole Kelvin. We're going to multiply it by moles. The moles cancels out. We're left with joules per Kelvin. Here's our products. We're going to subtract 1 times 69.91 joules per mole Kelvin. Again, the moles cancel out. That's our reactants. And we're going to get 118.8 kilojoules per Kelvin. So that's a positive value for our enthalpy of reaction. We're going from a liquid to a gas. We would expect the entropy to increase. So we would expect this value to be positive. We're going to do the same thing for B. It is a little bit more complicated, but look at the products first. Okay, you're going to find lead chloride times 1 and hydrogen times 1, and that's the sum of your products. Okay, that's what you'd put here. You're going to subtract 2 times HCl plus 1 times PB. And see what you get for your value, and then see if that value makes sense. So I'll give you a minute, plug those numbers in. And I modeled the first question. So show your work in the second question the same way. And that way you're much more likely to get the right answer. Okay, just kind of putting stuff in the calculator or doing half the work on the paper, it's more likely you're going to make mistakes. Okay, so just be careful, show all of your work and see what you get for the enthalpy, entropy change for reaction B. Okay, so we're going to take 1 times lead chloride plus 1 times hydrogen. So this is the sum of the products. We're going to subtract 2 times HCl plus 1 times PB. So this is the sum of the reactants. Okay, notice the moles cancel out. We're going to be left with joules per Kelvin. And we get negative 171.8 joules per Kelvin. Now, we can predict whether that makes sense. Well, we're starting with 2 moles of gas here. We're ending up with 1 mole of gas here. Well, that makes sense that we would expect the entropy to go down for the reaction, and it does. All right, so let's add on to that. We're going to talk about what's called Gibbs free energy. Okay, when we talk about the spontaneity of a reaction, sometimes it's hard for us to figure it out just by looking at the entropies, because we have to determine the entropy change for the system, we have to figure out the entropy change for the surroundings, and we have to consider what the entropy change for the universe would be. So what Gibbs did back in the late 1800s is he came up with a way to calculate the spontaneity of a reaction in a little bit of an easier way. He calculated the free energy that's available to the system when we look at a particular reaction. So this G value is what we call our Gibbs free energy. H is our enthalpy value, and T is temperature, and S is entropy. Now, if we want to calculate the change in free energy, we would just have to take the change in the Gibbs free energy value equals the change in enthalpy minus T delta S, or temperature times the change in our entropy. So this is a pretty big equation in thermodynamics. So where does it come from? Although you're never going to be asked to derive it, I do want to kind of show you that it is related to other equations. So if we were to look at our entropy for the universe equation, we know that the entropy of the universe equals the entropy for the system plus the entropy of the surroundings. Well, the entropy of the surroundings is equal to negative delta H of the system divided by our temperature. So we can just do a substitution here. Now, what we can do next is just multiply everything by T, or negative T. So this becomes negative T delta S of the universe equals negative T delta S of the system plus delta H of the system. And then if we define negative T delta S for the universe as our Gibbs free energy change, we get what we call our Gibbs free energy equation. Again, you're never going to be asked to derive it, but I kind of wanted to show you where it comes from. What's the importance of delta G? Okay, well, if we know delta H and we know delta S, we can calculate delta G. And if delta G is a negative value, we're looking at a spontaneous process. If delta G is a positive value, we're looking at a non-spontaneous process. And if delta G equals 0, we're at equilibrium. When we look at this Gibbs free energy equation, there's actually 4 different kind of scenarios that we can have based on what the sign on delta H is and what the sign on delta S is and how that affects the sign on delta H. The first 2 are pretty straightforward, okay? Let's say that we're given this reaction here, and we're told that delta H is negative 163 kilojoules. All right, so delta H is negative, gives us the number. Well, we're going from 1 mole of gas to 3 moles of gas So our entropy for our system is increasing. So delta S is positive. So look at this for a second. If delta H is negative and delta S is positive. Now temperature has to be positive because it's Kelvin. It's on the absolute temperature scale. Taking a negative value and subtracting a positive value can only give you a negative value. Delta G can only be negative if we're looking at an exothermic process that increases the entropy for the system. Delta H being negative, exothermic is enthalpy favored. A positive delta S is entropy favored. The reaction will always be spontaneous. Now let's look at the second example. Okay, we've got oxygen going to ozone. It tells us the delta H value is positive, so it's an endothermic process. That's not enthalpy favored. And if we look, we're going from 3 moles of gas to 2 moles of gas. So our entropy is negative. Our entropy is going down. So if we were to look at Gibbs free energy, if this value is positive and delta S, this value is negative, subtracting a negative is the same thing as adding a positive. So a positive delta H subtracting a negative delta S will always give us a positive delta G. So this process will never be spontaneous. It's always non-spontaneous. So it's not enthalpy favored and it's not entropy favored. It's not spontaneous. But let's look at the other 2 scenarios because they're a little bit tricky. Let's say that we're told we're taking liquid water and we're freezing it to solid water, and the delta H is negative. It's an exothermic process. So that means that it's enthalpy favored. It's exothermic. That's good. But the entropy is decreasing. That's not favored. If we look at Gibbs free energy, if our delta H is negative, and we're subtracting a negative, well, it's going to depend on the temperature, how big this value is. If we're at a low temperature, this value here will be smaller than this value here, and delta G will be negative and the process will be spontaneous. But if the temperature is high, this value here will be bigger. This T delta S value will be bigger than our delta H value. And subtracting a negative is the same as adding a positive. If the positive side is bigger, if it's entropy favored, delta G will be positive and the reaction will be non-spontaneous at high temperatures. So let's look at the opposite example. We've got liquid solid and we want to change it to gaseous solid. So now we're boiling water. Well, to boil water, we have to add energy in. So it's an endothermic process that's not enthalpy favored. But we're going from a liquid to a gas, so we're increasing the entropy that is entropy favored. So if we're at a lower temperature, the enthalpy value will be favored over the entropy value. Our delta G will be positive and the reaction will not be spontaneous. But if we're at a higher temperature, the entropy will be more a higher value than the enthalpy will be. The Gibbs free energy value will be a negative value. So the reaction is spontaneous at higher temperatures. So if enthalpy is favored, but entropy is not favored, it's temperature dependent. And the opposite, if enthalpy is not favored and entropy is, it's temperature dependent. If our entropy increases and our enthalpy increases, it will always be spontaneous. If the enthalpy is negative or is positive, it's endothermic, is not favored, and our entropy is negative, it's not favored, it will never be spontaneous. But if the entropy is favored and the enthalpy is not favored, the only time it will be spontaneous is at higher temperatures. And if the entropy is not favored, but the enthalpy is favored, the process will be spontaneous at lower temperatures. That's kind of what this graph tells us here. If we have an exothermic process that increases entropy, it will always be spontaneous. If we have an exothermic process, but we're decreasing the entropy, it will be favored at lower temperatures, but not favored at higher temperatures. If we have an endothermic process that decreases the entropy, it will never be spontaneous. But if we have an endothermic process that increases the entropy, it will be spontaneous at high temperatures and not at lower temperatures. Let's do some math. Okay, that was kind of conceptual. What is the normal boiling point of liquid bromine? At what temperature is the following process spontaneous? Okay, so liquid bromine going to gaseous bromine. Now we need to know some information about bromine. So this process is endothermic. We're going from a liquid to a gas. We know we have to add energy in order to break those intermolecular forces. So having a positive delta H makes sense. We're going from a liquid to a gas. We're increasing the entropy. So having a delta S value that's positive, this value makes sense. Now, a positive entropy favors spontaneity, but a positive enthalpy does not. So let's look at our Gibbs free energy equation, and we want to calculate the temperature. So we'll just do a little bit of algebra here. We're going to first define boiling point. Okay, boiling point is the point at which the liquid phase and the gaseous phase are at equilibrium. So delta G is going to equal 0. So we'll substitute in 0 for delta G. We're going to add T delta S to both sides. And then we're going to divide both sides by delta S. And that'll give us T. That's what we're trying to find. What temperature? So we have our equation that we figured out from this information. Now we're going to substitute in our information. So delta H, we're going to substitute in. Now I changed the units. Since this is joules per mole Kelvin, and this is kilojoules per mole, I just changed this to joules, so the units are the same. So I multiplied it by 1,000. So 3.10 times 10 to the 4th joules per mole. Okay, again, I just took kilojoules per mole and converted it to joules per mole. So there's our enthalpy value. We're going to divide it by our entropy value. Notice that now the joules cancel out. The moles cancel out. We're left with 1 over Kelvin, which gives us Kelvin. So T equals 333 Kelvin. So that means that this process will be spontaneous whenever the temperature is above 333 Kelvin. If we're below 333 Kelvin, then delta G would be a positive value and the reaction would not be spontaneous. So liquid bromine will spontaneously boil at a temperature above 333 Kelvin. So let's look at another scenario. Okay, we've got carbon tetrachloride. We're breaking it down into carbon and chlorine. It tells us that the enthalpy change for this reaction is positive 95.7 kilojoules. That makes sense. Positive means we have to add energy in. It's endothermic, and we're breaking bonds in the reaction. And breaking bonds is an endothermic process. And our delta S value is positive 142.2 joules per Kelvin. And that makes sense as well, because we're going from 1 mole of gas to 2 moles of gas, so we're increasing the disorder in the system. We want to calculate delta G, and then once we do that, we want to determine whether the process is spontaneous or not. We write down our givens. We know delta H, okay, it's endothermic. We know delta S, it's increasing the entropy. We know the temperature in Kelvin is 298. And then we're going to use our Gibbs free energy equation to calculate delta G. Now go ahead and do that, but look at your units and be super careful with your units. Okay, this is kilojoules. This is only joules. So multiply this number by 1,000 so that your units are consistent. See if you can calculate delta G and then figure out what that delta G value actually means. Okay, I left it in joules. If you convert it to kilojoules, that's great. Okay, so we're going to multiply this number by 1,000. So that gives us 95.7 times 10 to the third joules. We're going to subtract from that our temperature times our entropy value. The Kelvin cancels out. We've got joules. The joules are our answer. Again, if you change it to kilojoules, you would get 53.3. I agree with that. Okay, now the important part there is the positive. Okay, in the chat, if it's a positive delta G, is it endothermic or exothermic? Positive delta G. Because conceptually, we just have to know what the signs mean. Process at this temperature is not a spontaneous process. We would need to increase the temperature in order to get this reaction to actually occur. All right, so let's add on just a little bit to this. Okay, we're going to look at calculating the entropy or enthalpy, calculating the entropy, and calculating the Gibbs free energy. So we've got our reaction here, and now we have a table. Okay, the enthalpy values are things from Chem 1. The entropy values are things that we just went over. So let's look at the delta H first. So if we want to calculate the delta H for the reaction, if we want to find out whether this reaction is endothermic or exothermic, actually, if you look, it's pretty much the same reaction or equation that we had for entropy. It's the sum of the products minus the sum of the reactants. And we're multiplying them by the coefficients in the balanced equation. So here are your enthalpy of formation values. Here are your coefficients in the balanced equation. See if you can calculate delta H for the reaction. Don't go any further than that. Calculate delta H for the reaction. Look at the sign on delta H and try and figure out what that means with respect to the reaction. Okay, so I'm getting 2 times negative 396. That's the sum of my products. Minus 2 times negative 297 plus 1 times 0. The enthalpy of formation for oxygen is 0 because that's the free element. And you got to kind of be careful with the signs when you plug that in the calculator. And you're going to get an enthalpy change for the reaction of negative 198 kilojoules. The negative means this reaction is exothermic. It's giving off energy to the surroundings as it occurs. And that's enthalpy favored. That's good. So now let's calculate the entropy change for the reaction. Again, the equation looks just about the same. We're going to take the sum of the products minus the sum of the reactants. We're going to use the entropy values this time in our table. And we're going to be multiplying these values by the coefficients in the balanced equation because the numbers on the table are per 1 mole and sulfur dioxide has 2 moles, sulfur trioxide has 2 moles. So plug your numbers in, see what you get for the entropy change for the reaction. Look at the sign and see if that makes sense. Okay, so we're taking 2 times the sulfur trioxide. That's the sum of our products. We're going to subtract 2 times the sulfur dioxide plus 1 times the oxygen. And we're going to get a negative 187 for our delta S of a reaction, our entropy change for the reaction. Now let's look at that. A negative sign means our entropy is going down as the reaction proceeds. Well, we're starting with 3 moles of gas. We're ending up with 2 moles of gas. So that makes sense. That negative sign makes sense. The entropy is going down as the reaction proceeds. Now, the last thing we want to do is we want to calculate delta G. Well, we're going to take the value that we got for our enthalpy, that negative 198 kilojoules, and we're going to want to take the value that we got for our entropy, that negative 187 joules per Kelvin, and plug them into our equation. Now, the units don't match up. This is kilojoules. This is joules. It doesn't really matter which one we change. Okay, I would change the kilojoules to joules. It doesn't matter though. Okay, change them so they're the same. The temperature is in Celsius, so you need to change it to Kelvin. Plug the values into your Gibbs free energy equation. Calculate your value for delta G, and then look at the sign and determine what that sign means for the reaction. Actually, this time I kept it kilojoules. I changed this to kilojoules. So I'm going to take my delta G, my delta S, going to multiply it by my temperature in Kelvin. So my Kelvin cancels out. Now I've got kilojoules minus kilojoules. That works out well. You just get a bigger number if you converted them to joules. And we get negative 142 kilojoules. So what does that negative sign tell us about the reaction? It tells us that the reaction is spontaneous at these conditions. So the enthalpy is favored, it's exothermic. The entropy is not favored because we're decreasing the disorder in the system, but the overall energy is going down, which means that the process is going to be a spontaneous process.